11 files arrived on a honeypot inside a single 7-second SSH session. This episode works through all of them using only static analysis, file, readelf, and strings. No sample was executed at any point. That is not a safety caveat. It is the point. You can learn a great deal about an unknown binary before you run a single instruction, and a lot of what you learn tells you whether running it is even necessary. The session lasted 7.4 seconds. 3 commands arrived over SSH. The first read a known good system binary to fingerprint the CPU architecture. No compiler invoked, just a direct read of a file the attacker knew would be there. The second tried to fetch a dropper over HTTP. The third pushed 3,716,336 bytes straight down the open SSH channel into a temporary file. No outbound connection needed. Egress filtering that blocks HTTP does nothing here. 11 files remained when the session closed. The triage workflow has 5 steps, and the same 5 steps apply to every unknown binary. Identify what you have with file. Measure the actual size with WC. Check the ELF header with readelf to see whether the binary is packed or truncated. Pull strings and filter for what matters. Then decide. Apply those steps in order, and nothing you conclude requires executing anything. Here is the sample directory, sorted by size. The largest file is just under 9 megabytes. Below it, 5 files cluster between 1 and 2 megabytes. Then a half megabyte entry, a 32 kilobyte entry, 2 scripts in the low kilobytes, and 1 file that is 11 bytes. Step 1 is simply observing the shape of what arrived before drawing any conclusions about what any individual file is. File on the 2 smallest non-tiny entries. Both are shell scripts, readable directly, no obfuscation. The first is a launcher. It detects the CPU architecture, selects the matching binary from the payload set, runs it with a single argument, then deletes the copies. The second is an eviction script. It runs before anything else installs. Plain text, in both cases, the first tool in the workflow answers the first question immediately. The eviction script is the more telling of the two. Before anything installs, it removes immutable flags from the crontab directories. It expects that protection to be in place because competing malware uses it. It then filters every cron file and every shell startup file for the patterns other malware uses to persist. Get, curl, base64, and raw TCP socket invocations. It kills processes hiding under names 1 character away from real system tools. systemtd with a D at the end, and -bash. The family name appears in the launcher itself. It is Redtail. This is one criminal operation clearing another off the machine before taking it over. File on the 5 payload binaries. Each identifies as a statically linked ELF. 4 architectures appear immediately. x86, 64, i386, ARM 32-bit, and ARM 64-bit. The 5th is RISC-V. Reading the ELF header on the x86 64 binary shows 0 section headers. UPX strips them when it compresses the binary. Statically linked and no section headers together is the signature of a packed, self-contained executable that carries everything it needs. 5 architectures means the operator ships for every target they might land on, including a RISC-V build for embedded boards that put themselves on the internet. Statically linked means the binary carries everything it needs. No library version on the target matters. And because the pool address, wallet, and mining algorithm are baked in before UPX compresses the result, there is nothing to configure after deployment and no way to redirect the miner once it is running. Ship it, run it, done. The operator made every decision before the binary left their machine. This is an autonomous payload. Now the 3 files that look wrong. File on all 3 gives the same reading. ELF 64-bit, x86 64, dynamically linked, and a note that section headers are missing at a specific offset, the same offset on 3 files of radically different sizes. The tempting conclusion is that the section header table has been deliberately erased to confuse analysis tools. That conclusion is wrong, and recognizing why it is wrong is the most useful thing in this episode. Check the ELF header before you reach a conclusion about armor. The section header offset field declares that section headers begin at byte 30,302,232. The largest program header segment extends to byte 30,301,816. The declared section header location sits 416 bytes past that end, precisely where a compiler writes section headers after the final segment. The header is honest. The files are simply short. Two of the three sizes, 32,768 bytes and 524,288 bytes, are exact powers of 2. Compiler output is never an exact power of 2. Those are the read buffer boundaries of whatever tool attempted the download, visible in the truncation points themselves. readelf on the smallest fragment shows the full ELF header. The entry point, program header count, and section header offset field are all present and readable. The header is intact, even in 32 kilobytes. Then WC gives the actual byte counts for all three. The gap between what the section header offset declares and what the file actually contains shows exactly how far each download reached before it stopped. The smallest holds less than 0.1% of the full binary. The largest holds about 30%. That 30% turns out to be enough. Strings on the largest fragment. Filter for the Go runtime first. Go routine, scheduler, and map type descriptors appear with their full package paths. That alone identifies the language. This is not the C or C++ of the UPX set. Then the import paths, a PAM authentication library, an SFTP library, a hardware profiling library, and the Go Crypto SSH package. Then the minor configuration keys, pool address, username, algorithm, and nicehash flag. But unlike the UPX set, no values are baked in alongside those keys. The key names are present with nothing next to them. Then the server binding. The binary listens on all interfaces. It does not go anywhere. It opens a door and waits. And before it acts, it checks its own external address via a well-known lookup service. Here is the contrast. The UPX set is 5 interchangeable static binaries with configuration baked in. Deploy one on a matching architecture, and it mines. No operator input after launch. No way to redirect it. Nothing to intercept mid-flight that changes its behavior. The Go binary knows no pool, no wallet, no algorithm. Instead, it binds a listening SSH server, profiles hardware through a system library, detects virtualization environments, including KVM and LXC and container runtimes, reads its own external IP address before acting, and accepts a specific control command from an operator over that SSH channel. That is not a worm carrying a payload. That is an agent joining a managed fleet, and every characteristic that distinguishes it from the UPX set is visible in file, readelf, and strings without executing a single instruction. Static analysis stops here. It cannot tell you what configuration was delivered to any machine that checked in, whether a particular host received a mining assignment, or who operated the Go binary. It cannot determine whether any of these samples ran anywhere. What it can tell you, from file and readelf and strings alone, is the language a binary was built in, whether it is packed or truncated, what runtime or libraries it requires, whether configuration is baked in or runtime supplied, what network services it starts, and what external hosts it contacts before acting. For an unknown file from an unknown source, that is almost always enough to make a decision, without running a single instruction.